All right, let's see what's a transformer. A transformer is an electrical device that can increase the output voltage or decrease the output voltage, increase the output voltage or decrease the output voltage, right? A transformer works with electromagnetic induction. Electromagnetic induction. Transformer works with electromagnetic induction. A transformer is an electrical device that can increase the output voltage or decrease the output voltage. Okay, cantik. Next, number 2. Right? What is a transformer made of? Okay, a transformer is made of a primary coil. This primary coil must be connected to an AC supply. Okay, this primary coil must be connected to an AC supply. AC supply, primary coil, and the secondary coil, we call it as the output. This is the output. So we'll have first primary coil. We can put the number of turn NP primary coil. Secondary coil, number of turn, secondary coil. The primary voltage, P primary, and the secondary voltage, S. So a transformer is made up of primary coil, secondary coil. Number of turn in the primary coil, number of turn in the secondary coil. And there will be laminated core. The core is as usual soft iron. Soft iron core. So there's a soft iron core. But to build a transformer, it must be laminated, thin layer and insulated. The thin layer insulated is called laminated. Okay, done with this. Okay, you see here. See this one. Okay, when we use a transformer, see, there is a primary coil. There is a primary coil. Number of turn in the primary coil. There's a primary voltage. Primary voltage can be called input voltage. Primary voltage can be called as input. Input voltage. Okay. Then there's a secondary coil. Secondary voltage. Number of turn in the secondary coil. Secondary voltage is the output voltage. Is the output voltage. Okay. What happened? Let's see what happened. As the current flows in the primary coil. As the current flows in the primary coil, always remember primary coil must be connected to alternating current, AC current. As the current flows in the primary coil, around the primary coil, there will be electromagnetic field. Remember the solenoid? There will be electromagnetic field. The secondary coil, this is the secondary coil. This secondary coil is in the region of the primary coil's magnetic field, electromagnetic field. The secondary coil is in the region of the primary coil electromagnetic field. So what happened to the secondary coil? This secondary coil constantly undergoes changes of flux. When the secondary coil constantly undergoes changes of flux, the secondary coil started to produce what we call induced voltage or induced current. Induced voltage or induced current. I repeat the whole thing again. when current flows in the primary coil. When electric current flows in the primary coil will produce electromagnetic field. The primary coil, the solenoid, will produce electromagnetic field. The secondary coil is in that region. The secondary coil is in the region of the electromagnetic field. So secondary coil constantly undergo changes of flux. As the secondary coil constantly undergo changes of flux, the secondary coil started to produce its own induced current. Okay, next thing again. So if you see the diagram carefully, again, transformer must have primary voltage. This is the input. So as the primary current flows, when the primary current flows in the primary coil, around the primary coil, they will produce the electromagnetic field. The electromagnetic field can be produced in the air surrounding or even in the soft iron core So when the electromagnetic field is produced here, what happened here is that this secondary coil undergo changes of flux. When the secondary coil undergo changes of flux, the secondary coil will start to produce its own induced current. So now the secondary coil started to produce current, output voltage. Secondary is output voltage, output current. It's an induced current. We are producing current. So this is the third electromagnetic induction. First electromagnetic induction, The first electromagnetic induction was the conductor cut flux. Okay. The second electromagnetic induction was the flux cut the conductor. Okay. The third one is the transformer effect. We call it transformer effect. What is the transformer effect? See, there is no relative motion. Number 1 and number 2 has relative motion. Number 1 and number 2 has relative motion. This one do not have the relative motion. All right. Transformer effect, nothing is moving. Transformer effect, no movement. Transformer effect, no movement. No movement, therefore, no relative motion. There's no relative motion. But what happened here is that changes of flux occur. Changes of flux occur because of AC current. AC current. Okay, let's see all this again. The first two requires relative motion. Relative motion. The first two require relative motion. All right. The transformer effect, there is no movement at all. No relative motion at all. Then how does it occur? The flux will go through changes, or changes of flux occur because of AC current. Okay, now we call upon Suk Hui. Chai Suk Hui, lama tak jumpa. Chai Suk Hui. Suk Hui, how are you? Suk Hui, how are you? Oh. Joshua.
Yes.
Her Wi-Fi not good. Okay. Can't hear or don't know can hear or not. Oh, that's why she's not coming in for the class most of the time lah. Okay.
Yeah. Hello.
Okay, Joshua.
Yes.
Our Terence and his good buddy is not here, right?
Sure, Jashan
Really?
is here.
Jashan is here.
Where?
Tam Jashan.
Jashan?
Oh yeah, finally. Hi, Mr. Tam Jashan. How are you?
Past few classes also you got joined already, I saw.
Yes, sir, but my attendance tak ada pun. You all better update my attendance.
This is his first physics class that he attend, I think.
Physics class first one lah, Jaden. Because we too, remember Jaden, we too got underground message. We are connecting every day, checking attendance. Others all don't know about our secret society. Okay. Where is Terence? As usual, is below the radar lah. Terence is not there. Okay, never mind. Where is this Joshua? Joshua?
Yes.
Okay, so changes of flux. One is with relative motion. The other one is no relative motion. Understand?
Yes.
Okay. So if there's no relative motion, it's called the transformer effect. Okay, let's look at how the transformer effects work. Okay, all of us. See, okay, now. When we have a primary coil, okay, see here. The primary coil, right? See carefully, must be connected to an AC current. Let's say I label up here A and down here B. Okay. We haven't learned how to identify if, let's say, current flow from A to B, which one is north, which one is south. We haven't learned. I haven't teach you all. This is called Lenz's law. Belum ajar. Next week saya akan ajar ni. Okay. Okay, I want to finish all the electromagnetic induction first. Okay, now the idea here, let's say now current flow from A to B. Then later current will flow from B to A because this is AC current. AC current frequency is 50 Hertz. When the frequency is 50 Hertz, 25 Hertz, 25 times current flow from A to B. Another 25 Hertz or 25 times current flow from B to A. That's the idea of 50 Hertz. That's the idea of frequency is 50 Hertz, right? Current flow from A to B, then B to A. Okay, now, the idea here, as the current flows from A to B, katakan. Dengar dengan betul lah guys, this is example only. Let's say current flow from A to B. When the current flow from A to B, let's say I say up here is North Pole, down is South Pole. So listen carefully. If up is north, down is south, electromagnetic field will be like this. So if I place a secondary coil here, all right, the secondary coil will undergo changes of flux with North Pole up and South Pole down in the first 0.02 second. Remember, because 50 Hertz. 50 Hertz period is 0.02 second. I continue. I go through the whole thing again. First, number one, current flow from A to B, because this is AC current, in the first 0.02 second. If let's say, contohnya, up is North Pole, down is South Pole, electromagnetic field will cut the secondary flux. will cut the secondary flux up north, down south in 0.02 second. Next, current will change the direction. Current will change the direction. Okay. Okay, when current changes the direction, see what happened now. Okay. Now in the next 0.02 second, current changes its direction. Now current flow from B to A. Now let's say down is north and up is south. So electromagnetic field flow again, produce both sides, both sides. This electromagnetic field will cut the secondary coil. This time the secondary coil experience changes of flux down north, up south. So the secondary coil will produce its own induced current now. Its own induced current, let's say like this. All right, this is induced current. So in the first 0.02 second, the induced current might have flow up, because in the second 0.02 second, the induced current is flowing down. So the whole idea here is that, listen to me carefully, the whole idea here, whenever the current direction changes in the primary coil can experience AC current, A to B or B to A. If the current flow from A to B, the secondary coil experience changes of flux up north, down south, or terbalik. How to be terbalik? If let's say the current flow from B to A, then the secondary coil might experience down north, up south. So the secondary coil is going through continuous changes of flux. The secondary coil is going through continuous changes of flux. So it continuously will go through changes of flux. As the secondary coil continuously going to change of flux, there will be electromagnetic induction. The secondary coil started to produce induced current also with the same frequency, AC frequency of 50 hertz. Okay. So question time. Who got question? There will be a primary coil and there will be a, in the notes got, notes all in the note set gave already. Got, you check. I'll show you now in a while. You see, okay, now. Okay, I'm going through again. See, I'm going through again. Okay, let me go through again. This is the secondary coil. Secondary coil. So a transformer is an electrical device which can increase or decrease the output voltage, can increase or decrease the output voltage in the secondary coil. This is the secondary coil. Output voltage is called secondary voltage. This is the number of turn in the primary coil, number of turn in the secondary coil. The primary voltage are called the input voltage. The primary voltage are called the input voltage. So what happened in the primary coil? Current will flow with changing direction. This is called the primary coil. This is the primary coil. In the primary coil, current will flow with changing direction. As we learned earlier, the primary coil, as current flows in it, when current flows in the primary coil, as the current flows in the primary coil, we realize that around the primary coil, there will be electromagnetic field because it's a solenoid. So if you look at the secondary coil now undergo changes of flux. Any coil that undergo changes of flux will produce induced current. So inside here, induced current is produced. So induced current is produced in the secondary coil. This is also called electromagnetic induction, whereby the changes in the direction of current, in the primary coil, produce electromagnetic field, around the secondary coil, with changing direction of the pole, So the secondary coil constantly undergo changes of flux. The secondary coil constantly undergo changes of flux, and it will produce induced current. The induced current produced by the secondary coil also will have the induced current in changing direction. So induced current in the secondary coil also will flow in AC direction. If current flows one time to the right, constant changes of the electromagnetic poles on the secondary coil. Constant changes of the direction of the electromagnetic poles on the secondary coil will make the secondary coil to constantly undergo changes of flux. So secondary coil will constantly produce induced current, electric current. Okay, let's watch one video.
This is Super Cala.
A transformer is used to increase or decrease the voltage of an electrical supply. It's essential for transmitting electricity from a power station to your home, but it's also essential for using your mobile charger to adapt to 30 volt electricity from your main supply to the 5 volts needed to charge your mobile phone. In this video, I'm going to be looking at 2 aspects of transformers. First of all, explaining how they work, and secondly, showing you how to use the transformer equation. Physically, this is all the transformer is. On one side, you have a primary coil, that's wire that comes in, wrapped around and comes back out again. And on the other side, you have the secondary coil coming in, wrapped around and back out. On the primary coil, you would attach your supply of power, whether that's the power station or your main supply. And on the secondary coil, you'd attach whatever your load is. So that could be a mobile phone, or it could be something much bigger, some lights, or an entire building perhaps. In between, we have an iron core here. Now, what's really important to remember is that there is absolutely no current flowing through this iron core. The electricity is kept within the coils, and nothing flows between them. First, let's think back to when you studied electromagnets. If you run a current through a wire, through any wire, it sets up a very weak magnetic field around the outside of that wire. Now, if you wind that wire up into a coil, what that will do is it will squash together all of those magnetic field lines to create something like this. This becomes a magnet with a north pole here and a south pole here. To create an even better electromagnet, we just need to put an iron nail through the middle of that coil, and it will become a much stronger electromagnet. This is almost exactly how the primary side of a transformer works. The current in the primary coil flows around here. That makes the iron core into an electromagnet. Now, there's just one difference. Instead of using direct current that would flow continuously through our primary coil here, in a transformer you always have to use alternating current. The difference being that in alternating current, the electric current shuffles backwards and forwards 50 times every second in the coil, instead of just flowing in one direction. Now, this is really important because instead of creating an electromagnet with a north up here and a south up here, instead the north and south will switch around 50 times every second. So what was north will become south up here and north down here, and vice versa. 50 times a second, north and south will switch direction. Now, to understand how the secondary side of the transformer works, we need to think about how electrical generators work. When you move a coil of wire in a magnetic field, you will induce electricity in that coil of wire. That's how a generator works. Now, the clever bit about transformers is even though there's nothing physically moving, the core and the coils are completely stationary, the magnetic field that is in this core, or around this core, is switching direction 50 times every second. So as far as the secondary coil here is concerned, it is seeing a moving magnetic field, and so an electrical voltage will be induced in the secondary coil. The more wires we wind around the secondary coil, the bigger that induced voltage is going to be. That's where our transformer equation comes in, and we'll come to that in a moment. But you can see here the primary coil has fewer windings than the secondary coil. This means that the voltage will be increased by this transformer. Time for a quick summary then. We have 4 steps to success. First of all, an alternating current flows through the primary coil, and this creates a magnetic field around the iron core. But that magnetic field is constantly changing direction because that electric current is alternating. Number 3, the movement of the magnetic field induces a voltage in the secondary coil. That's working just like a generator. And number 4, the more turns of wire we have in that secondary coil, the bigger that induced voltage will be. So that gives us control over whether the transformer increases or decreases the voltage. Here is our transformer equation. All it tells us is that the ratio between the voltages on the primary and the secondary coils is equal to the ratio between the number of turns in the primary coil and the number of turns in the secondary coil. For example, if we had a primary voltage of 230 volts, that's the mains electrical voltage in the UK, and a secondary voltage of 23 volts, that would tell us that the ratio between the two needs to be 230 divided by 23, or 10. Now, if we have 1000 primary coil, we need to choose a secondary coil that has enough turns to make the same rate. So we want to show 10. So a secondary coil with 100 turns
Transformers are composed of an iron core ring wrapped in coils. One coil is connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives a transformer its unique electricity altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120 V. This results in a calculated step-down voltage of 60 volts.
Okay, we are back. We are back. Okay, now let's continue. Let's see our notes. We have all this in our notes. Last class, you see. Why last class? Explain what, you think? Explain what, I think. Oh, concave. Okay. Very slow, lah. Okay, transformer. Okay. So what are the formulas of transformer that we must know? Okay. Formulas of transformer that we must know. The formulas of transformer will be primary voltage over number of turn of primary coil equals to secondary voltage over number of turn of secondary coil. Okay. Power in a transformer as usual lah, P equals to VI. Power in a transformer, P equals VI. Okay, belum Maria. Oh, yeah. Almost like 10 not in yet. Yeah, but I said use what? So it should have come now what? Sorry lah, because just now it was disconnecting, then we don't have time. Only 10 minutes to go. Yeah, 10, 15 minutes only. Same Sean, same formula, Sean, same formula. Okay, this is how transformer formula works. Okay, first thing we must know voltage of primer over number of turn of primer equals to voltage of secondary over number of turn secondary. Same thing, Sean, see here. NS over NP equals to VS over VP. Same formula, what? The same stuff, just that I like to use like this. Okay. Power equals to VI, then we have step up transformer, output voltage secondary is greater, primary voltage lower, number of turn in secondary is greater, more, number of turn in primary is less. So step up transformer, number of turn in secondary is higher, number of turn primary is less. And then if I look at here, output current secondary will be lower, but primary is higher. Okay, then when we have transformers, if it is a step down transformer, secondary voltage is lower. Number of turn in secondary coil is less. Output current is higher. Step down transformer, output current is higher, secondary current is higher. Output is secondary, yeah? Okay, let's look at it here again. Okay. Who want to copy? Copy there, guys.
Wait, wait.
Wait.
Okay, copy first. Step up, step down. Copy first. Okay, done. Hello. Sudah ke?
Okay.
Okay, done. Okay, let's see here now. Okay, when you have a transformer, this time I explain, you talk to me, who don't understand, talk to me, okay. This is the primary coil, okay. Primary coil must be connected to AC current. Why AC current? Only AC current will produce alternating current. Current will flow from up to down or down to up, okay. And then we will have the secondary coil. The secondary coil is placed in the region of the electromagnetic field of the primary coil. In the region of the electromagnetic coil of the primary coil. All right. Secondary coil is connected to any electrical appliance. This is output. Output. Okay. We call Sean Wong. Okay. Primary coil, yes, will produce electromagnetic field. Yes or no? Yes, okay. Primary coil will produce electromagnetic field. Okay, now. So secondary coil constantly undergo changes of flux. Okay. Now we call upon Sean Kern. The primary coil, this primary coil is actually a solenoid, a coil. The poles of this coil, is it changing or static, Sean Kern? The poles of the primary coil, changing or static? Sean Kern, answer. The poles are changing or static? Static? No, it's changing. These poles will change because this current is changing. When the current flow from down to up, maybe up north, down south. When the current changes from down to up, maybe up is now is south, down is north. So what happened here is that the poles of this coil is changing. For a while north, south, then change. South, north. So the solenoid is not moving. All the solenoid are static. They are not moving. The coil, the solenoid, they won't move. In a transformer house, nothing is moving. Just that the magnetic field appear, disappear, appear, disappear, appear, disappear with changing direction. The electromagnetic field appear, disappear with changing direction. Okay. So the secondary coil will experience changes of flux with changing direction. So the secondary coil experience changes of flux with changing direction. So the secondary coil is able to produce induced current also with changing direction. The secondary coil will produce induced current with changing direction. So induced current is produced. Induced current is produced in the secondary coil with changing direction. Now we call Alim. Alim?
Yeah.
Okay. Can I build a transformer? My question, Alim, can I build a transformer? Okay. By using a direct current? Can or cannot?
Cannot.
Why? Your answer is correct. Cannot. Why?
Because there will be no change in flux.
Very good. Because this DC current will produce the magnetic field for once, and the magnetic field will be staying there constantly. It's a static magnetic field. Magnetic field will become static. When the magnetic field is static, the secondary coil does not undergo changes of flux. So secondary coil will experience maybe the first time when it was formed for a while, secondary coil undergo changes of flux. After that, secondary coil does not experience changes of flux. So the whole idea here, why do we need AC current to build a transformer? So that primary coil can constantly produce electromagnetic field with changing direction. So when the electromagnetic field is changing direction, the secondary coil constantly undergo changes of flux. So ada, tak ada, tak ada. And when ada for a while, it's in up north, down south. Then changing. You see, this is the secondary coil, right? The secondary coil first will experience electromagnetic field like this. Okay, up is north, then down is south. Okay, next, wait, check one, wait. Then this is the secondary coil. Now what happened? The electromagnetic field appear again, but now up, south, down, north. So if you see here, this electromagnetic field will cut the secondary coil with changing direction of the poles. So secondary coil will produce induced current also in changing direction. Induced current is produced in the secondary coil changing direction. Okay. Check Chuan asked me a question. Oh, AC and DC. Okay, see here, Check Chuan. If you have a, yes, Sean, every 0.02 second, the poles are changing. Yes, current direction changes. Yes, every 0.02 second because 50 hertz frequency. So first 25 times the current flow this way in primary coil. Then another 25 times the current flow this way in the primary coil. So primary coil every 0.02 second, secondary coil experience changes of flux in changing direction in every 0.02 second because the frequency is 50 hertz. So every 0.02 second, secondary coil constantly goes through changes of flux. That's why you cannot use the DC current. DC current flows only in one direction, constant one direction. So the magnetic field appear and stays there. It's not changing. It just appears static there. So secondary coil will not experience the changes. Secondary coil will not experience the changes. Okay, now. Okay. So check one, you understand what is AC and DC current or not? AC current fluctuate. AC current fluctuate. This is AC current fluctuating. DC current, okay, good, check one. Just flow in one direction, suggest it's not fluctuating. Okay, done with that part. Formulas done. So we look at here. Let's look at one example. Okay, now, let's say you are given one primary coil with number of turns 100. Then you have another secondary coil with the number of turn is 400. This was 100 and this 400. This is the AC current primary voltage input. If let's say the output voltage is 800 volt. So this is the secondary voltage. The output voltage is 800 volt, the secondary voltage. What was the primary voltage? So formula, primary over number of turn equals to secondary over number of turn. Primary voltage, don't know. Number of turn, 100. Secondary voltage, 800 volt. Number of turn, 400. So, primary voltage. No. Yeah, correct lah. So, potong. Yes. 200 volt. Very good, guys. Good. Okay. Next. These transformers, this is the formula. Okay. The power produced here is VI. The power produced here also VI. Okay, primary VI is primary and primary. Okay, power in the secondary coil also VI, but secondary. This can be called input also. This can be called input also. This can be called output also. Output and input. So this is input, this is output. Okay, done. Okay, one question. Let's see. Okay. We have one transformer. Okay. AC. Okay. Now what happened? Number of turn here. Primary is 20. Number of turn here, secondary is 40. So you all know this is a step-up transformer because number of turn of primary is lower, number of turn secondary is higher. So this is a step-up transformer. If let's say the primary voltage was 24 volt, all right, and then the secondary current is found to be 2 ampere. 2 ampere. Can you find for me, all right, the primary current or not? This is the secondary current, and we call this an ideal transformer. Okay, what is an ideal transformer? An ideal transformer. Hey, you all know lunchtime, right? Give me another 10 few minutes, can guys? Boleh kan? Okay. Okay, let's calculate that, Satish. If it's an ideal transformer, we will assume the input power is equal to the output power. If it's an ideal transformer, we assume the input power equals to the output power. Input power is VI. Output power also VI. But before that, we have to find the output voltage. So we know the formula Vp over Np equals to Vs over Ns. Primary volt 24, primary turn 20. Secondary voltage do not know. Secondary turn 40. So secondary voltage is 48. 48 guys. So what is the primary current? So use this. So we know now if it is an ideal transformer, it's ideal. Okay, good, Sean. Good. If it's an ideal transformer, input power equals to output power. So input voltage 24, input current don't know. Output voltage 48, output current 2. So the primary current was 4 ampere. Very good. 4 ampere. 4 ampere. Okay, done. So this is how transformer work. Okay, now answering my question time. We call upon Kavin. Mr. Kavin.
Yes, teacher.
If it's a step down transformer, which one will have higher voltage? Step down transformer.
The primary.
Okay, very good. Next one, we call upon Averil. Averil, how are you?
Yes.
Okay, Averil, apa khabar? Baik?
Yes.
Okay, Avril. If I look at step up and step down transformer, which transformer the output current is bigger? Step up or step down?
Step up.
Step down, Avril. In a step down transformer, secondary coil, the output will have bigger current because voltage decreases. Okay, next. Thank you, Avril. Next, we call Marcus. Marcus.
Yes.
Hey, Marcus, 2 days back, I drove, until the barricade they put there. I went out, I drove big times rock barricade they put, huh? Did you see or not? You know or not?
I never go out from my house.
Oh my God, you're a good boy, lah. You'll get award after this. Okay, Marcus, my question is, what is an ideal transformer?
Ideal. What?
What is an ideal transformer?
It's an electrical device which can increase or decrease the
Output voltage.
Yes.
Okay, that is transformer. Okay, that is the meaning of transformer. Very good. You just gave us the meaning of transformer. Transformer is an electrical device that can increase or decrease the output voltage. Very good. Now my question is, what is an ideal transformer? Okay, an ideal transformer, will there be loss of energy or not?
No.
Very good. That is why the input power is equal to the output power. So when we say it's a ideal transformer, we are telling input power is equal to the output power. So when input power equals to output power, Marcus, and there's no loss of energy, what do you think of efficiency, Marcus?
It's good.
Okay, it's 100%. Efficiency will be maximum 100% efficiency.
It's good.
So it's very good, very high efficiency. We assume it's 100%. We assume it's 100% efficiency. Clear? Okay,
yes.
now, thank you, Marcus.
You're welcome.
Okay, now if you all see here, wait, they use this photo now. Mana send me photo. Okay, okay. If you all see here, the transformer, there's a laminated core. See, there's a laminated core. Okay, this is soft iron. Okay, why are we using soft iron for a transformer core? Same like electromagnet, it can be easily magnetized and demagnetized. It can be easily magnetized and demagnetized. Easily can be magnetized and demagnetized. Give me another 2 more minutes, guys. 2 more minutes, okay? I can see some of you like want to run away from the laptop or handphone, whatever now. Okay. Easily can be magnetized and demagnetized. That's why we use the laminated core, soft iron core. So very easy to magnetize and demagnetize. And number 2, we know that once we use the soft iron core only, we can increase the strength of magnetism. Okay, now, so transformer, actual truth of transformer is that transformer is a device that can actually produce a lot of heat. A lot of heat. So the efficiency of a transformer normally is not good. So to overcome that problem, we use laminated core. Laminated core are very thin plates. This is actually very thin plates, very thin plates of soft iron. Thin plates of soft iron, laminated. Laminated, that means it is coated with insulation. Coated with insulation. Why there's a insulation there? So that they can reduce the current flow. You know what happened? Inside this soft iron, we supposed to produce current only in the secondary coil, guys, which is called induced current, right? Which is our output current. But what happened inside the soft iron also, a value of current can be produced. That current is called the eddy current. Some call it eddy. It's the eddy current. This eddy current is the current that is generated in the soft iron. And the problem with that current is a closed loop. See, it's a closed loop. When the current is produced in a closed loop, this current also can produce a lot of heat. This current also, not radiation, a lot of heat. Radiation for electrical system is the electromagnetic field. That's called radiation. It radiates in air. So that's called radiation of electromagnetic field. How many of you, guys, how many of you are the mechanical magnet with y'all? Siapa ada mechanical magnet? Do you have a mechanical magnet? Not the compass, or how many of you got compass, mechanical compass? I don't want the compass, your handphone one, the one digital. Fridge magnet, you can try fridge magnet. You take 2 fridge magnet, you bring to any cable wires, but be careful, don't touch the cable wires at all. And then see what happened to that magnet. You take a very light magnet, bring towards any cable wires like your aircon point, your house switch point there, the fuse box there, and try to put the magnet and see what happened to the magnet. The magnet will be repelled, man. There's a strong magnetic field around it. Remember the electromagnetic field? Right? It will be repelled away or attracted. Something will happen. If you have a proper compass mechanical, you can test all the cables in your house. Okay, that's all for today. I'll contact each class separately. Maybe this weekend we'll have one additional class for each classes. Okay, have a good day. Tomorrow we don't have class. Tomorrow is public holiday.